Okay, continuing on here in our description of atomic structure, we want to focus in on quantum numbers. Now, this is one, I think, of my favorite areas of chemistry because kind of something that happens in science is you will find what appear to be really complicated phenomena that actually are just a result of very simple rules working in conjunction with each other. And some other examples might be like the schooling behavior of fish, right? That looks like something super complicated is going on, but the fish are actually each following a very simple set of rules. Swarming of bees is kind of a similar idea. And I kind of feel like quantum numbers is the same thing. There are some basic rules with numerical values associated with them that explain the organization of the periodic table, right? So once we kind of understand these rules, now the rules are kind of made to fit what was observed about the periodic table. So if you think, well, why is that the case, right? Because that's the way the periodic table is. So the rules are the rules. Don't try to focus too much on, well, why do you start at 0 here and 1 here? The rules are the rules. Once you understand the rules, and they're very simple, those rules will reproduce the entire periodic table and give you the power to predict what would happen with future elements that might show up in the periodic table. Okay, so I'm going to go through the rules and I'm going to try to explain a little bit, how they give us the structure of the periodic table, and then we'll carry that into talking about electron structures. Or electron configurations, how we can kind of use a bookkeeping method to figure out where all the electrons are in a particular atom. Okay, the first quantum number is called the principal quantum number, and these are referred to numerically and by abbreviation in a lot of cases. So don't worry so much about remembering principal. This is lowercase n, and this is often just the first quantum number. This describes energy levels. Right, within the structure of an atom, and energy levels have to be integers. So the energy levels start at 1, and then you go to 2 to 3 to 4 to 5, etc. So n can equal 1, 2, 3, right, etc. But that's it, right? You start at n equals 1, right? Then you go to n equals 2, right? The second quantum number, so angular momentum quantum number, which is abbreviated with a lowercase l here. In fact, I'll usually write it as a script L, so it's a little more distinct from 1. When talking about this is often called the second quantum number. The second quantum number describes sublevels. So structure within each energy level. Right? So the values you get for L will depend on the values for N. So in general, L has values that start at 0 and build up to N minus 1. Okay? Now, again, this is to match what's actually observed. Don't, whoa, why is it 0? It's 0. It starts at 0, right? And I'll explain maybe why that is a helpful way to think about it as we get to that. But what this means is if we start with n equal 1, so the first energy level, right? N minus 1 would be 0. The only value possible for L is 0. So there's one sublevel in the first energy level. But if we go to the second level, if n equals 2, then, right, L starts at 0, but n minus 1 is 1. So there'll be a second value that corresponds to a sublevel in the second energy level. So n equals 2, the second energy level, has two sublevels. One where L equals 0, one where L equals 1. Now, there's a trend going on here. We go to n equals 3, the third energy level, we will add a third value of L. The third energy level has 3 different sublevels. And those sublevels will have different characteristics that we'll see as well, right? And so on. Fourth energy level has 4 sublevels. Fifth energy level has 5 sublevels, okay? Now, the first quantum number was numerical, and the second one was numerical. Well, the numbers can get a little confusing. So there's actually a way to account for values of L that uses letters instead. So let me try to put that over here on the side. So L equals 0, we call an S sublevel. Right, so instead of saying 0 for L, we say S. L equals 1 corresponds to a P sublevel. L equals 2 corresponds to a D sublevel. L equals 3 corresponds to an F sublevel. And then actually from there, it's alphabetical, right? L equals 4 is a G sublevel. L equals 5 is an H sublevel, etc. Now, eventually, you get to a point where you'd hit a letter you already used, like you might run into P again. I don't know what happens there, honestly. There's a point where these different types of sublevels are so far away from the nucleus that it's basically like they don't exist, or they're indistinguishable from the electron not being associated with the nucleus anymore. Now, we will certainly go up to G because the periodic table gets pretty close to G sublevels, so we will have to come back to this. Now, one way people like to remember this, right? SPDF is stupid people die first. That seems to be a memorable thing people can keep in their minds. So the first one is an S, the second one is a P, the third one is a D. Second one is a D, the third one is an F. And from there it goes alphabetically, so you don't really need a mnemonic for G, H, I, J. Hopefully you know your alphabet. So if we come back to this evaluation of the numbers, right? N equals 1, that means L equals 0. That means the first energy level, the only sublevel that it has is 1s, right? So 1 for energy level, S for L equaling 0. The second energy level, though, has a 2s sublevel, right, where L equals 0, and it has a 2p sublevel, where L equals 1. The third one has 3s, 3p, but it adds 3d. Right? And so on. When we get to the fourth energy level, now we'll have a value of L equal 3, which would correspond to an F sublevel. Right? And when we get to the fifth energy level, we'll have a value of L equals 4, which would correspond to a G type sublevel. Right? These different sublevels are integrated into the structure of the periodic table, right, in relationship to their energy. And it's, once you kind of see it, it's really kind of a cool thing. Okay, let's keep going and talk about some of the other values, and then maybe we'll try to kind of tie everything together a little more at the end. The third quantum number, right? So the technical definition here is the magnetic quantum number. The symbol here is lowercase m sub L, right? But often when you're discussing these, this will just be the third quantum number. But you should know the abbreviations here as well, m sub L. This corresponds to orbitals. So this tells us how many orbitals are in each sublevel. Okay, so where the electrons actually reside is termed an orbital, right? And there are orbitals within sublevels. So here's how we determine how many orbitals are in a sublevel. We take the value of L, and m sub L will have values starting from negative L, going up through 0, and then all the way up to positive L. Okay, so similar to what we did for levels and sublevels, if L is equal to 0, the only possible value of m sub L will be 0, because negative L would be 0, positive L would be 0. The only value, and these would be integer values as well. There's no partial numbers here. So if L equals 0, which is a 1s, or sorry, that's just an s. We don't know it's 1 necessarily there. M sub L equals 0. And that means one orbital. If there's one value of m sub L, there's one orbital in that sublevel. So any s sublevel, regardless of whether it's the 1s, 2s, 3s, or 4s, they just have one orbital in them. Now, if L equals 1, then m sub L now there can be a value of -1, of 0, and of +1, 3. orbitals would be present in those sublevels. So L equals 1, that was a p sublevel. So every p sublevel has 3 orbitals in it. And so on. There's a trend here as well. If L equals 2, m sub L now can spread from -2 through all of the integers up to +2. And that means there are 5 orbitals in every L equals 2 type sublevel, which is a d sublevel. Right? So 5 orbitals in a d sublevel. Right? When L equals 3, that is an f sublevel. Those will have 7 orbitals. When L equals 4, that corresponds to a G sublevel. Those will have, so for the G sublevel, there will be 9 values of m sub L, so there will be 9 orbitals. Okay. Now, we're going to see that in the periodic table as well, but let's try to get to the spin quantum number here before I have to shut off this video. The last quantum number, and this could be called the 4th, but usually this one is just called spin. Right, so spin magnetic quantum number, but usually we just refer to this as the spin quantum number. Its abbreviation is m sub s. This talks about orientation within an orbital. And there are only 2 possible ways an electron can be oriented within an orbital. So there's only 2 values here. This is equal to +1/2 or -1/2. And since this is referring to this kind of, the property has been labeled spin, it's kind of a weird quantum thing. It's not quite like, spinning around like a top. The value +1/2 is often referred to as spin up. The value -1/2 is referred to as spin down. Each orbital can only hold 2 electrons. If it does hold 2 electrons, the first one that goes into that orbital is spin up. The second one that goes into that orbital is spin down. Right? If we take those 4 rules and apply them, we can build up the structure of every atom in the periodic table, and even atoms that don't yet exist in the periodic table. Theoretical atoms, we can figure out what they should look like. And we'll do that starting in the next video.